So welcome back to discussion on electrostatics in matter. So this is our lecture 2, and today we'll start with the effect of electric field on molecule with inbuilt dipole moment. So what are the things that we have discussed till now is we can just revise. So we have just discussed what is meant by electrostatics matter. Like okay, so this electrostatics in matter is basically the study of a static electric field on insulator. So this is a basic thing that we are going to discuss. So for that, the first thing we have done is the effect of E on atom. So this we already discussed. And the second thing is the effect of E on molecule. So this molecule has of two types. So without inbuilt dipole moment, and second thing is this, the effect of electric field on molecule with inbuilt dipole moment. Okay, so what is the effect of electric field on neutral atom? So it just produces an dipole moment. So a dipole moment will be induced if you apply the electric field on neutral atom. And what is the effect of electric field on molecule? Again, that it induces an dipole moment. Okay, and there is some difference between when you're going from atom to molecules. In the case of atom, uh, the direction of dipole moment will be along the direction of the applied electric field. But in case of molecule, the direction of dipole moment may not be along the same direction of electric field. So that is the major difference. And in case of molecule, the equation connecting the induced dipole moment and electric field will become a tensor equation. So in general, this P equal to alpha E. So alpha is a scalar in case of atom, and alpha is a tensor in case of a molecule. So that is a thing that we discussed in the last lecture. So today we'll start with what is the effect of electric field on molecule with inbuilt dipole moment. So we can just erase these things. Okay, so we can take one example. So the molecule with inbuilt dipole moment. So the better example is water. The water molecule. So in case of water molecule, there is two hydrogen atom and one oxygen atom. So oxygen, the bigger one, and two hydrogen here to it. Okay, so this is oxygen, hydrogen, hydrogen. Now the angle between these is about 105 degree. So the hydrogen would be positive, and oxygen negative. So you'll get dipole moment along these two direction. So in general, the total inbuilt dipole moment will be along this direction. So it has some inbuilt dipole moment. Okay, so it is better to schematically represent the molecule with inbuilt dipole moment in another way. That is, you can show this as a negative charged atom and a positive charged atom separated by some distance d, and this would be your dipole moment p. This vector I can denote by symbol d, so that the dipole moment is equal to q into vector d. Now here, if you apply some external electric field, what would happen? So this is your molecule, and you applied some external electric field. Okay, so this is a system. So here the positive charge will experience a force towards right, a negative charge will experience a force towards left. So I can represent this as F plus, the force on positive charge, and force on negative charge. And what would be F plus? The F plus would be equal to the amount of charges Q. So F plus would be equal to Q into E, and F minus would be equal to minus Q into E. So therefore the net force would become zero. So the net force on the system would become zero. So will there be any effect? Yes, obviously there should be some effect. So although the net force becomes zero, but this molecule will experience a torque. Okay, so net torque is not zero. So how to find torque? So torque in general, the definition for torque is tau is equal to R cross F. So F is a force. Okay, and R is the vector connecting your reference point to the point on the application of force. Okay, so you can choose any point as your reference. Suppose you choose the center of the dipole as your origin. Okay, then this small vector I can represent is R plus, this vector I can represent R minus. So the charge, positive charge will experience a torque. So tau plus, that would be equal to R plus cross F plus. Okay, and what is R plus? Better I will use some other color. So this is your R plus, the vector connecting from O to the positive charge is R plus. So R plus, its length is d by 2, and the direction is along vector d. So vector d by 2. Similarly, what would be R minus? R minus is opposite to the direction of vector d. So this minus vector d by 2. Okay, so tau plus is R plus cross F plus. So R plus I have already written, vector d by 2 cross Q into E. Okay, so this is equal to half Q into D is nothing but P, half P cross E. So this is the torque on the positive charge. And what would be the torque on negative charge? The torque on negative charge is R minus cross F minus. So remember, R plus is vector D by 2, and R minus is minus vector D by 2. So R plus and R minus are the position vectors of the positive and negative charges respectively. So this become minus vector D by 2 cross minus Q into vector E. This minus and minus cancels, and you will get Q into D is again P. So it is again half P cross C. So what would be the total torque? The total torque is the sum of both R plus and R minus. So net torque, that will become just these two halves. If you add, you'll get P cross E. So that means if you exert a uniform electric field on a molecule with inbuilt dipole moment, then it will experience a torque rather than force. Okay, and due to torque, what would happen? Due to torque, the molecule will start rotating. So it will undergo a rotation motion, because we know that this torque I can write as I d square theta by dt square. The torque will produce an angular acceleration. So this will start rotating. So in which direction it will rotate? So this molecule will rotate in this direction. Okay. So if you apply a constant electric field or uniform electric field to a molecule, the molecule will start rotating. Okay. Now, will go under the complete rotation, or will it returns back to the previous position? So that we have to look into in very detail. So for that, we can go to the next page and we can copy this diagram better in order to save your time. Okay, so this is the case. Now, this is the step 1. Now in step 2, okay, so this molecule, if it start rotating, it will move along this direction. Okay, so after some time, the positive charge will reach here. In the meantime, the negative charge may reach here. That is after rotation from the original position, and this would be your dipole moment. Okay, now the force on positive would be like this, and force on negative would be like this. Now, what would be the direction of rotation then? If this is the case, then this will start rotating along this direction. So that means this molecule will not undergo complete cycle, the complete rotation. It will reach at some point, then it will go back to the original orientation. So that's the thing. So that means this molecule will start vibrate. Okay, not vibrate, basically it will start oscillate. So this will undergo an oscillation. Okay, so initially the molecule was along this direction. From here it rotated like this, reached this position, then it will go back to the original orientation. So it will start rotating in these two orientations. Okay, so this will start rotating like this. So it will undergo an oscillation. And now, which is actually the equilibrium position here. So the equilibrium position is the torque 0 point. The torque 0 would happen if the dipole moment are aligned in the direction of electric field. So if the dipole is like this, then torque is 0. Okay, but even though if the torque is 0, the molecule may not become stationary here. It will not take rest here, because while moving from the original orientation, it will acquire some kinetic energy when it reaches this position. Then it will move to the next direction. Okay, that would happen. This example is if you take the simple pendulum. If you release a simple pendulum at some certain angle from the vertical, it will not uh, become at rest at its equilibrium position. It will oscillate, it will move towards the other direction and will start oscillating. So similarly here the molecule will start oscillating about its equilibrium position. So this is the equilibrium position. Now this equilibrium position will have the minimum kinetic energy. Okay, so this orientation, the torque becomes 0 when P is parallel to E. Okay, and so that is called the equilibrium position, or it is the position of stable equilibrium. And around this stable equilibrium, this molecule will start vibrating. Not vibrating, it will start oscillating about its equilibrium position. Okay, so the molecule will oscillate about stable equilibrium position. Now, if you want, you can calculate the angular frequency of this oscillation, or this angular frequency, obviously depending upon the electric field and all. So that better you can calculate it. That you can do as an homework. Find angular frequency of oscillation of molecule under static electric field. Okay. Now here my question is, since it is under oscillation, I have to find the potential energy of the system. Okay. So that is my aim. So how to find potential energy? So consider the torque on a molecule is P cross E. So if you take the magnitude of torque, which is simply P E sine theta. So if theta is the angle between the electric field and dipole moment, I can write torque equal to P E sine theta. So then we can calculate what is the work required to move the particle or the molecule from some angle 0 to some other angle theta. So this work I can write as tau d theta, and if you calculate it, you will get PE, and the integral of sine theta would become minus cos theta and limit 0 to theta, and so this become minus cos theta 1. So this become PE into 1 minus cos theta. Okay, the potential energy P into 1 minus cos theta. Now this work done, I can always write as the final potential energy minus initial potential energy. Now, in order to calculate, in order to get the expression for the potential energy, the first we have to set the 0 point, the reference point of potential energy. So what we'll do is we'll set the potential energy equal to 0 when theta equal to 90 degree. So that means when the dipole moment, that is a dipole moment perpendicular to electric field. So when the dipole moment P is perpendicular to electric field, we set the potential energy 0. So this is our choice. We can choose any point or any orientation has 0 potential energy. Like you can logically you can think about the gravitational problem. So in gravitational problem, the 0 potential energy of gravitational system you can choose anywhere as you want. So you can choose the surface of Earth as 0 potential, or you can choose the top of a building as a 0 potential. That is up to you. So depending upon the problem, for the easiness of problem, you can choose any point as your 0 potential energy point. Okay. Similarly, here we have a choice. Either you can choose uh, theta equal to 90 degree 0 potential point, or theta equal to 0 is a 0 potential point. That is up to you. And since our textbook chooses theta equal to 90 as the 0 reference point, so I am choosing the same reference. That's it. If you want, you can do it some other way. Okay. So then we can calculate what is the work done to move the system from 0 angle to 90 degree. So from 0 angle to 90 degree, okay, I can write that would be equal to small pe 1 minus, instead of theta, I can put 90 degree, and that would be equal to the potential energy. Okay, but okay, since I already using pe for the dipole moment and the electric field, so for potential energy, I think better I choose some other term. I can put u. Okay. So set u equal to 0 when theta equal to 90 degree. So this is the final is 90 degrees. So the potential energy at 90 degree minus the potential energy at 0 degree. So this should be equal to small p into E, because cos 90 is 0, equal to the potential energy at 90 degree is 0 minus the potential energy at 0 degree. So that means the potential energy at 0 degree, I can write minus p into E. Okay. So since I have chosen the potential energy is 0 for at theta equal to 90 degree. I am getting the potential energy as minus P into E for theta equal to 0 degree. So remember, theta equal to 0 is equilibrium point, is stable equilibrium point, and a stable equilibrium point will have minimum potential. Okay, the stable equilibrium point will have a minimum potential. Okay, so here we are getting a maximum potential at 90 degree. So at 90 degree, you are getting 0. And okay, so obviously when you're going to 180 degree, if you put theta equal to 180 degree, what would be the potential energy? So you at 90 degree is 0. Can you guess what would be the potential energy at 180 degree? Obviously it would be plus P into E, and that is a maximum, and plus 180 degree, that is when the dipole moment is anti-parallel to the electric field, so that to again an equilibrium, and that is an unstable equilibrium, isn't it? Because when the orientation is 180 degree, when the orientation is 180 degree, the dipole will not experience any torque. Okay, because torque is what is torque? The torque is P cross E. So if the P and E are parallel and as well as anti-parallel, the torque will be 0. Okay, so torque would be 0 when theta equal to 0 degree or 180 degree. But theta equal to 0 degree is the stable equilibrium. The stable equilibrium means if you just replace it from theta equal to 0, it will come back to theta equal to 0 orientation. But theta equal to 180 degree is an unstable equilibrium. I think better I will just draw the two diagram and explain why one is stable and other is unstable equilibriums. Okay, suppose okay, let initially minus charge, positive charge, okay, minus Q and plus Q. So here the dipole moment and as well as the electric field is parallel. So if you just displace it from this orientation, what would happen? If you just displace it from this orientation, then plus would come here and minus would come here. The dipole would be like this. Okay, but here what would happen? This will experience a restoring torque, and it will try to move back to its original orientation. Okay, now in this case, the second case, suppose the dipole moment is anti-parallel to the applied electric field. So again torque is 0. So this theta equal to 0 degree and theta equal to 180 degree. So again torque is 0. So since torque is 0 and force is 0, it will have equilibrium, but this is not stable equilibrium. The reason is if you just displace it from this orientation, then positive charge may come here, negative charge may come here. Dipole will be like this. It cannot remain like this. What would happen? This positive charge will experience a force this direction, negative charge will experience a force this direction. Then this will start moving in the same direction. It will just rotate in its displaced direction, and that means it cannot come back to its original orientation. So it is not going back to the original orientation. That is not possible. it will move away from the original orientation. So that is why the second orientation theta equal to 180 degree is an unstable equilibrium, and this is stable equilibrium. So here the potential energy would be minima, and here the potential energy would be maxima. Okay, so now what I have found is the potential energy at 0 degree is minus PE. So then from this I can calculate the potential energy at any angle. So remember the work done from 0 to theta, how will I write? That would be equal to PE into 1 minus cos theta, and that can be written as the potential energy at theta angle minus potential energy at 0 degree. So this is equal to PE 1 minus cos theta, the potential energy at theta degree, minus potential energy at 0 degree is minus PE. So minus into minus become plus PE. So here we will get two term PE minus PE cos theta. So one PE would cancel, this one and this would cancel. So finally what is the result? The potential energy at theta angle is equal to minus P into E cos theta. Remember theta is the angle between the dipole moment and the electric field. So I can write this as minus P dot E. So the potential energy, the final thing is the potential energy at angle theta is equal to minus P dot E. And sometimes it's also known as the internal energy of the molecule. Okay, so it is called the potential energy or internal energy. Okay, I think this is a very straightforward derivation to you. Now the last thing is if you have a non-uniform electric field applied to a molecule with inbuilt dipole moment, what would happen? Okay, so if electric field is non-uniform, then the force experienced by the positive charge and the negative charge may not be the same. Okay, so if you have non-uniform electric field, then positive charge will experience some force F plus, that I can write Q into the electric field experienced by E plus, and for negative charge F minus is equal to minus Q into the electric field experienced by the negative charge. Okay, then what would be the net force? So net force would be the sum of these two, so that would be equal to Q into E plus minus E minus. Okay, so this is I can write a change in E. Okay, so this the electric field here and the electric field would be a slight difference, so that difference would be equal to I am putting as delta E. So I can write the net force as Q into delta I. Now it is possible to rewrite this expression using gradient, because uh, the change in some vector quantity along some x direction, I can write its its uh, gradient along x direction dot the distance. So this vector d is a distance. So this is the result of vector calculus. Okay, so remember this delta is a gradient. This is I think we have already done in the first semester, that is the the change in some scalar function phi, okay, I can write as del phi dot the displacement, maybe if the displacement is r, del phi dot r. The same thing is written here, but in the notation that we have already used. So therefore, in general, what would be the change in the total electric field? It will be the sum of all these changes, the change along x direction plus change along y direction plus the change along z direction. And I think it is possible to write this equal to d dot del acting on E. So therefore, the net force, I can write Q into d dot del acting on E. Now Q into D is nothing but dipole moment. So dipole moment dot del times E. So if the electric field is non-uniform, then it will experience a net force. So similarly, it will have torque. Obviously, it will have a torque, but the expression for torque would become slightly complicated. Okay, so that's it for the discussion for the time being. So today, what we have discussed is what is the effect of electric field on a molecule with inbuilt dipole moment. So first we consider a uniform electric field. So in case of uniform electric field, okay, remember, so this here we have considered uniform electric field. So that means the strength of electric field same at every point. Okay, so in case of uniform electric field, the net force acting on the molecule becomes zero, but you'll experience a torque, and due to torque, the molecule will experience a angular acceleration and it will start rotating. Now the problem is when it rotates, it may not come back to its equilibrium orientation. So due to the torque, it may start oscillating about the equilibrium orientation. And the net torque, we have seen that net torque is equal to P cross E. And there is two equilibrium orientation. One is stable equilibrium orientation and unstable equilibrium orientation. So we can calculate the angular frequency of the oscillation of the molecule when you apply a very uniform electric field, if you want. So that is I have given as an homework to you. And then in this problem, we have to calculate the potential energy or the internal energy of the system. So here the work is done by the electric field. So the change in internal energy or the change in potential energy is due to the work done by the electric field. So the work done by the electric field I can calculate by integrating the torque over the angle theta. So the torque is simply Pe sine theta, and if you calculate the work done, we'll get Pe1 minus cos theta. Now we have to connect this expression with internal energy. So for that we use the work energy theorem. So according to work energy theorem, the work done I can write the change in internal energy if there is no kinetic energy at initial and final point. So U final minus U initial is gives the work done, and we'll set the internal energy is zero, our potential energy is zero at theta equal to 90 degree. Okay, so this is our choice. We can choose any point as your 0 point. So since we choose theta equal to 90 degree as your reference point, so what you will get is the potential energy at 0 degree is equal to minus P into E. So remember, P is the magnitude of dipole moment and E is the magnitude of the electric field. Okay, and with that we can found that the internal energy of the system at an angle theta can be as minus P dot E. So this when P and E are along the same direction, we'll get minus PE, and if the P and E are along the opposite direction, then the potential energy would become plus PE. Okay, so at opposite direction, the potential energy is maxima because that is the unstable equilibrium, and if the P and E are parallel, and if they are along the same direction, the potential energy is minima. Okay, And finally, we have also calculated what would be the force on the molecule if the electric field is non-uniform, that is electric field changes with position. Then the expression for the net force, we can write P dot del times E. Okay, so we can stop it here. So in next class, we'll discuss what is the electric field produced by a dipole, and from that we can calculate what would be the interaction among the dipoles. It's the force exerted by one dipole to the other dipole, and so on. And thereafter, we'll introduce a new concept called polarization. So we'll see in the next lecture by the electric field produced by a dipole and numericals related to it. So thank you.